Hi, and welcome back to the fourth of our five-part video series on trade wind inversions. In this video, we're going to take a look at the first four forcing terms to the lapse rate tendency equation, as they're a little bit simpler to evaluate than our remaining terms, which deal with cloud processes as well as diabatic heating. So let's go ahead and dig right on in. So recalling from last time, we have the lapse rate tendency equation. We introduced this as having six forcing terms. So on the left-hand side here, which I'm highlighting here, we're looking at the change in the lapse rate, gamma here, as a function of time. And it has six forcing terms, A, B, C, D, E, and F here. And we described in our previous video just ultimately what those six forcing terms looked like, but we didn't say anything about how they actually contribute to the lapse rate itself associated with the trade wind inversion. Do these forcing terms strengthen or weaken the inversion? Do they change where it is located, particularly within the vertical? And that's the focus that we want to give to these last two videos in this sequence here. So as we do so, keep in mind that we're evaluating this equation at inversion height, roughly 800 to 900 hectopascals, where we have the inversion, not at some location way high in the troposphere, not right at the surface, but rather near to where we actually see the inversion being found. So we start back in with our term A, which was the nastiest of the four terms that we're going to consider in this lecture, looking at the differential due to its relationship to the vertical wind shear, horizontal potential temperature advection, given that we have a velocity dotted into the gradient of the potential temperature. And we're focusing just on the horizontal component of that term here. So again, this quantifies potential temperature advection by the vertical wind shear, so we ultimately need to know two things in order to be able to evaluate this term. One, we need to know what the vertical wind profile is to be able to compute the vertical wind shear. That's what we see here before the dot product. And ultimately, we also need to know this large-scale potential temperature gradient in order to be able to compute its advection. What we'll do is focus on this second term here, because we'll be able to show that we only really need to know that one. And because we know that one, we're not going to have to go into this vertical wind profile or the vertical wind shear term. And I'll show you just what that means here as we go forward with this term. So coming to this vertical cross section through the inversion, from Honolulu here at left to San Francisco here at right, we have this gray shaded region that I'm highlighting now as the region of our inversion. Each one of these solid black lines here is one of our isotherms, and we're looking at regions that are separated by about 500 to 600 kilometers from every single vertical line that we have through the diagram here to give us a sense for the spatial scale. So there's two key points to keep in mind when we're interpreting and reading data from here. Since we're out over the ocean, height in meters, which is what our vertical axis is here, equals nearly the same pressure everywhere. The ground down here is at 0 meters everywhere. There's no difference, at least not a very significant difference, in terms of the height of the ocean from one location to the next. And so when we see 500 meters, that's going to be about the same pressure everywhere, minor meteorological changes notwithstanding. Same for 1,000, 1,500, all the way up to 3,000 meters. So we can view any one of these horizontal surfaces, like this one here at 1,000 meters, being akin to a constant pressure surface as well. Why do we need to know that? Because on constant pressure surfaces, isotherms overlap with the isentropes. We can think about this in terms of Poisson's equation that relates potential temperature to temperature. The only other thing in there that's not a constant is pressure. But if we're on a constant pressure surface, it too is a constant. So this change here at 1,000 meters from 18 Celsius that we see where I just put the X to 16 Celsius, where I just put that next X, is going to be a 2 Kelvin potential temperature difference on that same surface. So a 2 Celsius change in temperature here is going to be equal to a 2 Kelvin change in potential temperature there as well, which really helps us be able to interpret that gradient of potential temperature that we have within this forcing term. So keeping this in mind, once again, note that the differences between these locations are about 500 kilometers apart. So we're looking at very large scale analysis here. So if we look, say for instance, between those two sites that I highlighted near to the inversion at 2 kilometers above ground level, with the 2 yellow spots that I've highlighted there. There's not a very large change in potential temperature between those 2 locations. The isotherm here is very nearly horizontal. And we could go over here to this location here at about 1,750 meters. It's a little less horizontal, but it's still quasi-horizontal. Could come down here 1,500 meters above ground level. Again, it's a little less horizontal, but it's still a very small change on the order of 2 Celsius or less, 2 Kelvin or less change in potential temperature per 500 kilometers from one of these vertical lines to the next. And so ultimately we can use this information to say that this forcing term is small. It's sufficiently small for us to be able to neglect this term. And so I really hope that this sound and visual comes through on your end too, because it's time to pull out our inner Steve Harvey and go, all right. With that in mind, we can move on to the horizontal lapse rate advection term, term B within our equation. And this one's a pretty straightforward term. We have a velocity dotted into the gradient of the lapse rate here. So we need to know the velocity and we need to know the lapse rate, and in particular how the lapse rate is spatially oriented relative to the velocity in order to be able to infer this term. And fortunately, we had analyses within our climatology a couple of videos ago that give us this particular information. But before we get there, there's one thing to keep in mind. By definition, advection can only move existing features around. You can't move something that's not already there. So I have my water bottle and I can move it around. I can advect it by the wind. But if my water bottle's not there, it doesn't matter if the wind is here. So I can't just create a water bottle out of nothing, much as I might want to from time to time, but I can't do it. So this term can't cause an inversion to become stronger or weaker. It can only cause it to move. And in this case, that would be horizontally move. So let's take a look at how this term might actually work in this regard. So again, going back to our climatology, we had this average temperature increase, which is related to the strength of the inversion. Keep in mind that the inversion had about the same depth, 400 meters everywhere. So what we have here is the change in temperature. So this diagram here ultimately gives us the change in temperature. And this depth here is the change in height. But ultimately, because the change in height is very similar to the change in pressure, just in the negative sense, and because we're out over the ocean, this change in temperature is roughly the same as the change in potential temperature, we're looking at the information that we need to know to be able to quantify the strength of the inversion. And thus these contours that we see here with our 4 Celsius, 6, 8, 10 Celsius, and so on and so forth, give us a measure of the inversion's strength, and thus a measure of the lapse rate changes associated with the wind field here. And so we know that the inversion is strongest near to the west coast of North America and becomes smaller as you head out here closer to Hawaii. And so we have a gradient where you have larger lapse rate here near to the coast and smaller lapse rate out here over the open oceans. We also had our low-level streamlines from our previous climatology with our area of high pressure out here in the central portion of the Pacific Ocean. And so in association with this, we have flow that is directed largely from north-northwest to south-southeast near the coast of North America. But remember, our contours were largely oriented from north-northwest to south-southeast along this coastline. So here and near to the coast of North America, there's no particular change, no particular advection, because the wind blows parallel to those contours in this region. But as you get further to the west from there, where this velocity starts to deflect back to the west, away from the coast, we start to get a wind component that blows away from the higher values of lapse rate, the stronger inversion, to locations of weaker inversion. And so we're going from larger temperature changes over here within our purple shaded region to smaller changes further offshore. And so consequently, we're trying to advect the larger potential temperature increases, the stronger inversion further to the south and to the west. So ultimately, this horizontal advection attempts to result in a stronger trade wind inversion over these open waters between California and Hawaii, blowing from large values of lapse rate toward lower values of lapse rate. And that's ultimately the key contribution from this term. It doesn't do a whole lot near to the coast of North America, but it tries to strengthen the inversion out here over the open waters, where it is relatively weak compared to the coastal regions. So what does lead to a strong inversion in the coastal regions? And what perhaps keeps the inversion from being particularly strong out over the open waters? For that, we have to dig into some of our later equation terms. So let's go to term C. This one's still relatively straightforward. It is a vertical lapse rate advection. So we have a vertical velocity and we have a change with respect to pressure of the lapse rate that we see here. One of these days I'll probably get a little bit better at drawing with this highlighter, but I hope you get the idea from what I'm doing here. So really, to compute this, all we need to know is the vertical velocity, and remember, we can assume that this is downward. We're in the descending branch of the Hadley cell circulation. Earlier in this video series, we showed why we would expect to see descending motion within this region. And so given that we can assume that it's downward, what we really need to know is the vertical distribution of the lapse rate here. And that vertical cross-section in the previous slide helps us with that information. But again, keep in mind, vertical advection can only move existing features upward or downward. If I have my water bottle again, advection can push it upward or bring it downward. But if I don't have my water bottle, I can't create a new water bottle out of nothing, ultimately. And so again, just like the horizontal advection term, this is going to change where things are located vertically, whereas horizontal changed where things are located horizontally, but it can't specifically strengthen and can't specifically weaken the inversion in any of those locations. It can only move it around. So going from here, we can even take a step back from that vertical cross-section. We can look at just one location. We can look again at our typical sounding from Southern California during the summertime months. And we have our inversion layer, which I'm highlighting here in yellow, with our temperature trace underneath that region here. And we know that we have downward directed vertical velocity. So ultimately, in the most simplistic of conceptual frameworks, what this is going to do is try to push that inversion closer to the surface, as the animation with the blue line that I'm highlighting now here attempted to show. It's trying to push that layer closer to the surface. If you had ascending motion here, what it would do is try to lift it to higher and higher levels. So again, it's just trying to push features upward or downward. If you really want to test your knowledge, a good way would be to take this information and the vertical lapse rate advection term itself from the mathematical formulation that we have on the previous figure, that we have earlier in this video and in the previous video, and actually prove this, not just this analytical evaluation that I've done here at left, but the actual mathematical evaluation. There's a key hint that you have here. Evaluate this term at two levels. One at the top of the inversion and two at the bottom of the inversion. And if you do that, you'll be able to see just how that would lead to a weaker lapse rate here, less positive, at number 1, and a more positive lapse rate here at number 2. That'll be a good question to consider as we get into the discussion forums, or perhaps even a quiz for this material. All right, so we come finally to our last term in this series, which is our divergence term. And so far, we have had 3 terms, one of which we neglected, and 2 of which we said can only move things around, horizontally or vertically. Now we get to a term that can actually strengthen or weaken an inversion, and we'll show how as we go through this process. So again, we have our lapse rate that shows up here, and we have this partial derivative of omega with respect to pressure that shows up here. And in our previous video, we said that this term is directly related to the divergence. Divergence itself equals this minus d omega dp on an isobaric surface through the continuity equation. And so we can mathematically or analytically interpret this term as simply the lapse rate times the divergence here. But that doesn't tell us a whole lot about how divergence itself can lead to a stronger or weaker lapse rate. It's a horizontal motion, so how would divergence that's spreading away from somewhere necessarily strengthen or weaken the inversion there? Or if the wind is coming together, how would that necessarily strengthen or weaken the inversion there? And so we'll look at this term physically first by looking at the vertical variations in vertical motion, the actual formulation of the term that we have here. But then we can look at it analytically as that product of the lapse rate and the divergence that we have there as well. So taking a look at this term in terms of our physical interpretation. So we're going to look at large-scale descent above the inversion with near zero vertical velocity below it. So you're looking at large-scale descent associated with the descending branch of the Hadley cell coming even all the way to the top of the inversion. Whereas down here at the bottom of the inversion, we're going to assume that the large-scale vertical velocity is near zero. We're in a different air mass. We're influenced by the properties of the surface and not by the large-scale descent of the descending branch of the Hadley cell circulation here. So in this context, we take some of the properties that we considered from why subsidence leads to an inversion and apply them here. So for instance, we could take this here at about 850 hectopascals, 1.4 kilometers above the surface, and with our downward directed vertical velocity, we can cause this air parcel to sink. And doing so, we follow parallel to a dry adiabat. Whereas down here at the bottom, here at around 960 hectopascals, we're not going to do anything. There's no vertical velocity at play, and so the profile will remain unchanged here. So if we do that, we ultimately end up getting the following line that we see here in orange that I'm going to highlight here in dark red. What's happening at the bottom is nothing. Nothing has changed. But following down the dry adiabat from 1410 down by a few hundred meters gives us this new profile with the ending point here with the X that is an even stronger inversion. So if you have descent that is very strong above and becomes weaker as you go below, ultimately you're going to cause your inversion to strengthen. Whereas it's pretty easy to think that if you had ascent that was stronger above, you're going to try to lift out that inversion compared to what you see here in the opposite scenario. So descent that becomes smaller as you go closer to the ground leads to a stronger inversion, as we can demonstrate here through this figure. If we come back to this more analytically in nature, however, we can revisit this low-level streamline plot with our anticyclone that we have here over the central northern eastern Pacific Ocean. And we have our flow that is directed in an anticyclonic fashion, but it is also difluent along the west coast of North America. And so our divergence in this region is strongly positive. And we know that our lapse rate within this region is also positive. Potential temperature rapidly increases with height through the inversion. So you have a positive lapse rate with a positive divergence associated with the difluent flow of the subtropical anticyclone. So the product of those two is positive, and consequently, mathematically, we can show that this term leads to a stronger inversion, just as we did physically on the previous slide. Keep in mind, this term is the single largest contributor to a stronger trade wind inversion of all of the terms that we will consider. So we can envision the trade wind inversion as primarily resulting from vertical variations in vertical motion. Strong descent associated with the descending part of the Hadley cell that terminates above the top of the boundary layer or at the top of the boundary layer that pushes that temperature profile downward, creates a more stable layer on the interface between the free atmosphere and the boundary layer beneath, ultimately leading to that inversion. The height at which that occurs varies from one location to the next. We'll look at some of the forcing terms that influence that as we get to our next video, the final one in our sequence. But otherwise, all we have left from these terms that we've looked at in this video is something that pushes it around horizontally or causes it to lift or rise vertically. Horizontally, there's not a whole lot going on. Vertically, it depends on just what the vertical velocity looks like through the inversion. So coming to the end and summarizing here, we neglected our differential horizontal advection term. Our Steve Harvey X from Family Feud caused us to get rid of that term. But if we look at horizontal advection, we said that this helps to strengthen the trade wind inversion between California and Hawaii. The wind blows from areas of higher inversion strength toward areas of lower inversion strength. But in that region along the west coast where it is already strong, the wind is largely parallel to those lines of constant inversion strength or constant lapse rate. So there's no real impact that occurs there. Vertical advection, however, attempts to push this trade wind inversion closer to the ground. We have large-scale descent associated with the Hadley cell circulation, and though that weakens as you get to the bottom of the inversion, which becomes crucial for the divergence term, it is still nevertheless descending through the inversion within the regions that we're considering. So this term is trying to push things closer down to the ground. But it's that vertical variation in the vertical velocity manifest through divergence that we see along the west coast of North America that is that single largest contributor to a strong trade wind inversion. And this one is maximized just off the west coast where you get that greatest spreading apart of the winds on the east side of the subtropical anticyclone. So with all that in mind, we have just two terms left. We have a cloud motion term, and we have all 5 of our heating terms that we still have to consider. We'll do so in our next video to wrap up our discussion of trade wind inversions. Until then, thanks for tuning in.